Hi everyone. I just wanted to go through question 34 from this year's exam to show how we can use this as a learning opportunity, but also a few aspects to be careful with and to avoid, and to go through some of the advanced theory that underpins the physics around the idea of orbital transfers and the nature and context of this question. So in this question, we're presented with a satellite that is orbiting the Earth at a particular radius. Then there's an instantaneous burning of the engines, and that sends it out on an elliptical orbit. There's a gain in kinetic energy in order to do this from burning the engines, which as a consequence has an increase in velocity. Part A of the question is quite straightforward. To analyze qualitatively the energy changes as the satellite moves from P to Q. That's quite easy. We've first of all had the burn of the engines. You've got chemical energy going to kinetic energy. And then as it moves further away from P to Q, so more in line to answering this question, that kinetic energy is converted to potential energy as it goes to a greater distance from the Earth. And that's in line with the law of conservation of energy. Problems, however, arrive in question 34B and also in 34C that we'll look at later. In 34B, we have to show that the kinetic energy of the satellite at Q is 1.194 times 10 to the 10 joules. And that is using the information here, in particular, the distance of Q from Earth, as this value here, 6.850 times 10 to the 6 meters. Unfortunately, this value for the kinetic energy and this value for the distance are incorrect for the value of the kinetic energy addition that was introduced with the burn of the engine here, as we'll show shortly. Fortunately, however, students wouldn't actually be discriminated against if they use these incorrect numbers, but they use them correctly. So they can follow the correct method and actually show that this is the kinetic energy at that particular distance. In the video by Paul from Physics High, he changed things such that saying that Q wasn't actually straight through at the apogee rather than Q was around here. So we have P at the perigee, which is the closest distance to Earth, as the focus or one of the foci of the ellipse. And we have Q is the apogee in this diagram. We know this because we've got a straight line through the Earth from the closest distance in the ellipse to the greatest distance. And in Paul's video, he suggested that we could actually get this answer by swinging Q around, which indeed is one way to solve this if we are to take these numbers as being correct. I'm actually going to take a different tack. I'm going to assume that the diagram is correct, but I'm going to show what the values should be. I'll also later on show how we can actually determine what that angle is, where Q would be for this kinetic energy and for this distance. So what we have here is what's called a Hohmann transfer. Now, this is the classic transfer that is used to send a satellite from one orbit to another orbit. Now, for this question, we're only using half of the Hohmann transfer. So if you've got a satellite around Earth and it's at a particular radius, we're calling it radius 1 here, it will have a particular gravitational potential energy, a particular kinetic energy, a particular orbital velocity. If we give it an additional injection of kinetic energy to increase its velocity, that increase in velocity, or delta V, will then push it out into an elliptical orbit, providing that increase doesn't take it beyond the escape velocity. We'll discuss that later. So that'll push out into an elliptical orbit, and then it will fall back in here, unless, of course, once we reach the apogee here, we have another burn to achieve the orbital velocity at this new altitude here. So in order to look at the change in velocity and the total velocities in general, we have to consider the law of conservation of energy for the orbital transfer. So we know from the law of conservation of energy that the total gravitational energy equals the kinetic energy, a half mv squared, plus the gravitational potential energy, minus big G, big M, little m over r. So this equals this expression here, where A is the distance to the semi-major axis. So that is half the distance between P and Q, half the distance, more specifically, between the perigee and the apogee. It is essentially the average distance of the satellite anywhere in its orbit from the Earth. Now, this equation, this equality can be reduced here for v squared to what is called the vis-a-vis equation, where mu is just gm, big G, big M here. Now, following this equation, we actually get the equation for home and transfer orbits. What we're concerned with is just the first part. We're just worried about delta V here because this is the scenario of the question. So we need to determine what delta V is. So ultimately, we can determine what the true value of R2 is, because this is the crux of this question. So we've got to determine what this distance of Q actually is. So we know the kinetic energy at P is equal to the total energy minus the gravitational potential energy. So this value is a half mv squared. The velocity at P originally, when it's in circular orbit, is now we need to determine the kinetic energy after the burn of the engine to ultimately get the new velocity. So we can ultimately determine delta V. So we add the extra kinetic energy as mentioned in the question, and that gives us a kinetic energy of, and this is of course equal to a half mv squared, where v is the new velocity, the increased velocity. And so this new velocity equals, so our change in velocity equals 167.47 meters per second. I've been abbreviating some of the numbers just to write them down, and so we've had a bit of inconsistency with significant figures here. When we follow this through, it's actually quite forgiving in the end, actually, in terms of the significant figures, but yeah, here is the value that we'll be using. So now we can substitute this in to determine R2. So root big G, big M over R1, in this case, is 7,728.61. So then we can substitute in R1. Now, with some very careful rearrangements, we can actually get down to determine that R2 should in fact be 7.314 times 10 to the 6 meters. So that's a lot bigger than the 6.850 times 10 to the 6 meters. So this has quite profound consequences. And so using this, we can now determine the new kinetic energy as it should be at Q. In order to do that, we first of all have to work out what the potential energy is at Q. So this was the methods that was suggested correctly in part B, but albeit using the values that were in the question. And so the kinetic energy is equal to the total energy, the new total energy, minus the potential energy. So the new total energy, don't forget, we've got to add in the delta V, the extra kinetic energy that was added to begin with, associated with the delta V. So one thing you could do is reproduce this question and just put in new values for the kinetic energy at Q and a different value for RQ, okay, or R2 within this diagram. So you could follow that through, and then all future students wouldn't really notice the difference, just warn them away from what is published out there. The main challenge we have as teachers, though, is around question 34C, which asks us to explain, or ask students to explain the motion of the satellite after it passes through Q. Now, this should be straightforward, as has been mentioned, and we'll talk about a bit more in a minute. It should continue the ellipse back in an elliptical orbit, but the suggested answer in the marking criteria is quite different. The suggested answer is that the velocity at Q is determined using these incorrect values, and then comparing that velocity with the orbital velocity, and therefore deducing, since the orbital velocity at this, the velocity of the satellite at this point is greater than the orbital velocity, is going to keep flying out further. Now, that physically couldn't happen. I don't want people to be worried here. This was just the published sample answer. Almost certainly this wouldn't have been used in the actual marking. So marking tends to use a lot more deliberation and don't actually necessarily even see these later published sample answers. They'd be working off the correct physics that I'll be going through now, where the satellite has to move back in. But this is in the public domain now, and so we've got to be careful that we don't use this as the answer. The best way to explain all of this is actually using a simulation from Andrew Duffy from Boston University. So this is absolute gold for explaining all of the orbital energies and the idea of the conservation of energy, and also to explain why that sample answer can't actually be true, and what actually happens in scenarios with elliptical orbits and changing orbits and the like. So this simulation from Andrew Duffy, when something is moving at its orbital velocity, it moves in a circle. We can see the velocity vector, we can see the centripetal force vector perpendicular. We can actually see that the kinetic energy is positive. The gravitational potential energy is negative and is actually twice the magnitude of the kinetic energy. And that the total energy is, in fact, half of the gravitational potential energy and is the negative of the kinetic energy. So all of these things are very interesting. And more to the point, moving in a circular orbit, they are all constants. Now, if we were to go faster than the orbital velocity, what actually happens is the total energy remains the same. We're not burning any engines. We had an instantaneous burn, like in the question. Now, that velocity is too great to stay within that circle, so it throws it out further. But gravity all the time is working on this satellite and trying to pull it back in. And so it's slowing up, it's losing kinetic energy, and that is being converted into gravitational potential energy, the total energy remaining the same. So we can see this as it progresses in the graph. And so it's left the perigee here, and it's just getting to the apogee here. And then it is moving perpendicular to the line of the force, and it is at the maximum potential here. Okay, it hasn't got the potential to go any further. So gravity is going to take over and start pulling it back in. And so its kinetic energy is going to increase and its potential energy is going to decrease, with the total energy remaining the same, obeying the law of the conservation of energy. So going back to that part C, we've had this half of the ellipse described. You know, what happens after point Q, which should be here. Well, this is what happens after point Q. It cannot go any further. And more to the point, never in any elliptical orbits at the apogee can the velocity at the apogee be greater than the orbital velocity. It's not even equal to the orbital velocity. That's why it falls back in. That's why in that Hohmann transfer diagram, you had to have a second burn here to remain in the circular orbit out here. And so, if you like, the scenario, once it gets there, once it gets to Q, it doesn't even have the orbital velocity to maintain that radius. So it's certainly not going to maintain that radius, and it absolutely isn't going to move further away. It's actually less than the orbital velocity for that radius. So it's actually going to do this, the equivalent of, obviously the scales all out of kilter. It's going to fall back in from Q back to P. Again, the total energy remains the same. And we've got this interchange between the potential energy and the kinetic energy. Okay, so now it's going back out to Q, and then it's going to fall back into P. And it's a stable elliptical orbit a la Kepler's first law, albeit Kepler's first law was about planets and the sun. Gravity works the same. It's elliptical orbits here with the satellite and Earth. And so a better answer for C, explain the motion of the satellite after it passes through Q, would be something like this. Having passed through Q, the apogee or maximum distance from Earth, hence maximum gravitational potential energy U, the satellite will continue in its elliptical orbit, a mirror image of the outward trajectory, a la Kepler's first law, getting closer to Earth and speeding up, continually converting potential energy to kinetic energy back to P, but the total energy remaining constant as per the law of conservation of energy. So we are describing its motion. It is elliptical. It is moving back from Q to P. It's getting closer to Earth, and the velocity is increasing. And so again, when you're going through this with your students, please don't use that sample answer. Obviously, use something of your own creation if you wish. But either way, make sure that we are showing and maybe even adding to the diagram as we have done here, that after Q, it is going to continue the ellipse back to P. And so for some bonus material, let's have a look at what angle Q would actually be if it was presented at the distance in the question and the kinetic energy in the question. So we can actually use this equation here for the polar coordinates in an ellipse, where r is the distance from the focal point, one of the focal points, which will be Earth, and obviously theta is the angle. Now, A, we said, is the semi-major axis, so it's the distance from A to C or C to B, just halfway along the major axis. And then we got E, this value E here, which is the eccentricity of the ellipse. E, the eccentricity, equals C over A, where we've said what A is for the semi-major axis. So C is the distance from the focal point to the center of the ellipse. So we can work this out as the distance of the semi-major axis minus the distance of the perigee divided by the distance of the semi-major axis. Now, everything is times 10 to the 6, so we can kind of simplify things by just going that comes out as 0.043813. And so we can now determine theta, seeing that we know from the question that the distance of Q is given as 6.85 times 10 to the 6 meters. The numerator in this expression works out as 6.9935 times 10 to the 6 meters. and that's over 1 minus e cos theta. And so theta comes out as 61.4 degrees. So it's up to you if you want to go into this detail with your students, but you can just make the point that the angle is around about 60 degrees for those kinds of values. And you also have the true values that we calculated. And the interesting point that for a particular increase in kinetic energy, you're going to get a particular increase in velocity called delta V. And a specific delta V gives rise to a specific increase in distance at the apogee. So it determines the shape of the ellipse of the elliptical orbit. And so if you want any further information on this topic and the background to this question, here are some references. And you can always find me at CrookED Science, and we'll be doing a whole heap of professional learning NESA accredited in term 1 and 2 around this year's paper, including question 34. So thank you for your time. Hope you enjoyed this. Any feedback, any questions, always welcome. Please do contact me, and hope to see you around, and I hope you found this useful. Take care.